When you first start learning AWS VPC, it all looks quite simple. You create a VPC, add a public subnet and a private subnet, attach an internet gateway, and launch an EC2 instance. At that point, you might think, that wasn't too difficult. But once you begin building real systems, you realize that VPCs have a few hidden rules. These are the small details that can leave a server without internet access, quietly increase your AWS bill, or create a networking problem that becomes very difficult to fix later. So, let us walk through 5 VPC lessons that most beginners only discover after something has already gone wrong. Let us say you launch an EC2 instance inside a subnet called public subnet. You configure the security group, try to connect to the instance, and nothing happens. The server is still unreachable. At this point, you may be wondering, but it is inside a public subnet. Why can't I reach it? Here is the important thing to understand. AWS does not care what you named the subnet. You could call it public subnet, internet subnet, or super public subnet. The name changes nothing. For the subnet to be public, its route table must send internet traffic to an internet gateway. The EC2 instance also needs a public IP address, and the security group must allow the connection you are trying to make. So, when an instance inside a public subnet is unreachable, check the route table, the public IP address, and the security group. The real lesson is this: a subnet is public because of how it is configured, not because of what it is called. Now you may be thinking, okay, that makes sense. I will just move my application into a private subnet instead. And honestly, that is usually a good security decision. But private subnets introduce another issue that many beginners do not notice until the AWS bill arrives. So, let us move on to number 2. Your application is now running inside a private subnet. That means someone on the internet cannot connect directly to the server, which is exactly what you want. But the server may still need to download updates, install packages, or connect to an external API. So you add a NAT gateway. Everything starts working and you move on. Then, at the end of the month, you look at the AWS bill and think, why has the cost gone up? The NAT gateway is usually the reason. A NAT gateway has a running cost, and you are also charged for the data that passes through it. The design can become even more expensive when resources in different availability zones send traffic through the same NAT gateway. It can also create a larger failure point if too many resources depend on one gateway. This does not mean NAT gateways are bad. They are very useful. But before sending all private traffic through one, ask whether some of that traffic could stay inside AWS by using a VPC endpoint. For example, if your server only needs to reach services such as Amazon S3, a VPC endpoint may be a better option. The lesson here is simple. Do not add a NAT gateway without understanding what traffic will use it and what that traffic will cost. Okay, so now the public subnet is configured properly and the private subnet has outbound access. Everything should work perfectly now, right? Well, not always. There is another part of the VPC quietly deciding where every packet should go, and one small change there can affect several systems at the same time. That brings us to number 3. Imagine someone is troubleshooting a connection problem. They open a route table, change one route, and the original problem is fixed. Great. But a few minutes later, 3 other systems stop working. Now everyone is asking, how did one small route change break so many things? The answer is that those subnets were probably sharing the same route table. Every subnet uses a route table, and that route table decides where the traffic goes. It can send traffic to an internet gateway, a NAT gateway, another VPC, a VPN, or an on-premises network. The problem begins when several different types of subnets are all using the same main route table without anyone realizing it. You make one change for the public subnet, but that same change also affects the private application subnet and possibly the database subnet. A cleaner approach is to separate the responsibilities. Use a public route table for public subnets, a private route table for application subnets, and give database subnets only the routes they genuinely need. That way, changing one route is less likely to break several unrelated systems. At this stage, your routes may look correct, and the traffic appears to be moving in the right direction, but sometimes the application still does not respond. You check the route table, it looks fine. You check the security group, that also looks fine. So, what else could be blocking the connection? This is where number 4 becomes important. Security groups and network ACLs can look as though they are doing the same job. Both control network traffic, but they behave very differently. A security group is stateful. That means when an allowed request reaches your EC2 instance, the response traffic is automatically allowed to return. A network ACL is stateless. It checks the incoming request and the outgoing response separately. So, your request may successfully reach the server, but the response can still be blocked on the way back. That is why a connection can fail, even when the security group appears to be correct. A useful way to remember the difference is this. Think of the security group as a shield around the EC2 instance, and think of the network ACL as a gate around the entire subnet. Both can be useful, but complicated network ACL rules can make troubleshooting much harder, especially when return traffic or temporary ports are blocked. So, when traffic reaches the server, but the response never returns, do not only check the security group, check the network ACL as well. Now, our VPC is connected, the routes are organized, and the security controls are working. But there is still one decision that can create a much bigger problem later. At the beginning, it looks like a small detail. You may not notice the problem until you try to connect your VPC to another network. Let us finish with number 5. When creating your first VPC, choosing an IP range may not feel very important. You may simply use 10.0.0.0/16 because it is familiar and easy to remember. Everything works, so you continue building. Then, a few months later, another team creates a different VPC using the same IP range. Their system also works perfectly on its own. The problem only appears when someone tries to connect the two VPCs. Because the IP ranges overlap, AWS cannot clearly determine which network should receive the traffic. This can block VPC peering and create problems when building a larger network with services such as Transit Gateway, and fixing it later is rarely simple. You may need to create new subnets, move applications, replace IP addresses, or rebuild an entire VPC. That is why IP planning should happen before the first server is launched. Give production, non-production, shared services, and future environments their own planned ranges. It may feel like a small decision today, but good IP planning can save weeks or even months of work later. So, those are 5 AWS VPC lessons that many beginners discover only after something breaks. A subnet is not public just because of its name. A NAT gateway can quietly increase your costs. A shared route table can affect several systems at once. Security groups and network ACLs do not behave in the same way, and poor IP planning can block future growth. Before building your next VPC, take a moment and ask 4 questions. Where could this design fail? How could it be improved? What will it cost? And how is it secured? That is the difference between simply creating AWS resources and designing a network that is ready for real production use.